Good afternoon. Oh, Sarah is here.
Hello.
Hello.
Hi, Magali. How are you?
All right. What about you?
I'm doing great. Thank you so much.
Great. Okay, they are coming, and it started recording already. So what I need to do is to share to make you the host.
Yes, that'll be okay.
Yeah, and now how did I do that this morning? so there's a place to do that. Okay. So I think it's here. Oh, see, multiple participants can share simultaneously. Okay, so that might be what I should do in the future. So I set it up that multiple participants can share the screen at any given time. So you can start, well, it's 2 o'clock, you can start working. Just share your screen and it's all yours.
Sure. No problem. Thank you so much, Magali. Appreciate it. All right. So let me see. I guess they can see it now. Okay. All right. Well, where did it go? Close this. Close this. And close this. Here we go. All right. All right. So first of all, thank you so much for the invitation. Happy to be here and happy to provide this lecture. Um, it's a little bit tricky to bring this lecture into a workshop format without the um, correct resources. And because of COVID-19, it's kind of tricky to go and create accounts in the cluster. So we're going to do the best we can. So this is going to be a friendly introduction to GPUs and their impact in science. So I'm going to bring things that are fairly complex into, let's say, friendly and approachable terms, and hopefully you guys will be able to understand this. The idea is not for you to be an expert about GPUs once this presentation concludes. The idea is for you to understand that there is a new element called the GPU. The idea is for you to understand what this element can do. The idea is for you to understand the basic difference between the regular and traditional processor that a computer has versus this new computing element, and to allow you to understand some of the benefits that this new computing element is bringing into science. All right. With that being said, we're going to talk about what is GPU accelerated computing. The very first question that you guys might have is, what is a GPU? The GPU stands by Graphic Processing Unit. Many years ago, there was a couple of guys in Silicon Valley that they decided to create something to accelerate video games. So they say, well, you know what? Video games, it's an industry that is perhaps going to produce a lot of money in the near future. So why we don't get together and we create a company and our product is going to create a new device that is going to be inside the computer and is going to help the CPU, the central processing unit, to accelerate computation and accelerate computation in order to give video games a more realistic experience. So this company is known as NVIDIA. Okay, I'm going to be writing here. Okay, so NVIDIA. NVIDIA was born many years ago, and NVIDIA created the very first GPU. Very first GPU. Um, what is the GPU going to do for you? Well, as I mentioned before, the GPUs are supposed to accelerate video games. Okay, that was the very first intent. However, video games is nothing else but something that in computation is known as multimedia. Excuse me, multimedia. And in multimedia, you have to do two things at the same time. At the same time, you are going to be doing processing of audio and video. What does this mean? For example, if you are playing video games and you shoot a bullet, you want to hear the bullet at this moment that it was shot, not 5 seconds later, because that's not going to be realistic. So for the gamer, from the perspective of the gamer, it's simply a game. From the perspective of the computer scientist and the scientist behind the GPU, is a problem, computing intensive problem. So video games, the video games that you are playing at home are video games that benefits from resources, hardware that are going to be capable of doing a lot of computations per unit of time. So that's what we are making reference to computational intensive applications, which is this right here. All right. With that being said, we move on to the next one. So your computers and the video game console that you guys happen to have at home, these computers and all the computers, your cell phone calculators, they process a different type of numbers or different formats to represent these numbers. One typical traditional format is the integer numbers. Integer numbers is a number like 1, like 2, like 10, or 100. Any other number like this is going to be considered an integer. And there is going to be another set of numbers known as the floating point numbers. What are going to be floating point numbers? Floating point numbers are going to be numbers such as 1.1, 2.2, or pi. This is number pi. 1.0, you might say, hold on, 1 is the same as 1.0. Maybe for you, maybe for us, for human beings, we will understand this difference. However, computers, they don't understand this. A computer understands this as an integer number, and a computer understands this as a floating point number. So in the world of computers, these two are different. For the world of humans, these are the same, okay? So floating point numbers are going to have some advantages because in reality, in the real world, many of the problems that computers are going to solve for us will be using floating point numbers. Imagine you guys doing science. Imagine you guys doing basic physics. Imagine you guys doing basic mathematics. Imagine you guys solving something as simple as the area of a circle without being able to use floating point numbers for pi. So if we are constrained to the world of integer numbers, you will be obligated to say pi is equal to 3 because you cannot say 0.14, 15, 92, 65, 4. Okay, so computers provide a mean for us to represent this kind of things. So in reality, in science, most of the problems are going to be dealing with this type of data that you see here, which is going to be floating point numbers. All right, going a little bit further, floating point numbers can be divided into two big groups. One is going to be called single precision, and the other one is going to be called double precision. I am not going to go deeper into this, but what I want to tell you is single precision provides a certain amount of digits after the decimal dot, and double precision provides many more. So the more precise is because you are using double precision. The less precise is because you are using single precision. What does this mean? We human beings, we can say, give me all the digits of pi. So we can say 3.14, blah, 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 and we can continue forever. Okay, we human beings can do that. A computer cannot. A computer is actually a finite element. It's going to have, it's going to be an element that is going to be constrained to finite resources. So inside the computer, there will be some spaces, which is going to be in memory, where these numbers are going to be represented, and you are going to have just certain amount of elements to save those numbers. You are not going to have infinite of this. So this is a small size, and this means the large size. To put it simple, and what is important about this slide, and what I want you guys to understand from this slide is, when you are working with computers, you are going and you are, and when you are working with computers and you are doing science, you are going to be working with these numbers, not necessarily this. There are very few, very, very, very few problems that will make exclusively use of integers. Integers can be combined with floating point numbers, but most of the problems that you are actually going to solve in science will require floating point numbers. All right, with that being said, we go for this graph. Now you might ask, what is this? I don't understand this. Well, I'm going to bring your attention to these curves that you see here, and then I'm going to explain what is going on. So of course, this axis right here, the x-axis, this axis right here is time. And this axis that you happen to have here is going to be something different. It's going to be gigaflops per second. Gigaflops is the number, the is, okay, let me do this. Giga is 10 to the 9. Okay, if you are familiar with this kind of notation, 10 to the 3 and 10 to the 6, and then you have 10 to the 9. So this is what is known as a kilo. This is mega, and this is giga. So this is 10 to the 9 flops. This is floating point operations per second. So what this graph is showing is how many of those 1,000,000,000 operations per second with this type of numbers can be done. And this graph is comparing multiple resources. This graph right here, this blue, and this other blue graph are graphs associated with a CPU. So your computer at home, has the CPU.
The end of the month.
And this one right here is for a CPU. And this one here is for another CPU. Let's call this CPU 1 and let's call this CPU 2. So this one is going to be this CPU 2. And allow me to put this right here, CPU 2. And this is going to be CPU 1. So as you can see, these CPUs can solve the problem. They can deal with massive amount of data. But look at this one right here. This one and this one right here. The higher it means you can do more per unit of time. So if we rephrase the question and we ask who is more efficient, you guys are going to say this. And the answer is why. The question to the why answer. What is the answer? The answer is more efficient because you can do a whole lot more things per unit of time compared to this one. Comparing this one in this particular date, you will see the difference. It's a very strong, drastic difference. So GPUs can do a whole lot more, a lot more than CPUs. Okay, that's the idea. Now, let's talk a little bit about the differences between one and another. The CPU, this is what you are going to have in your computer, and it's very likely that, or by now, it's very likely that your computer will have a GPU. Maybe you have an NVIDIA CPU. The CPU, this CPU that I'm making reference here is what we call the processor. And very likely that in your computer you will have something like an Intel i3 or maybe Intel i5 or maybe Intel i7 or maybe by now Intel i9. So your computer, the processor in your computer is going to look like this. You are going to have some important elements. I am not going to talk that much about these elements, and I'm going to focus on these green elements. Think about these elements as your workforce, and I'm going to ask you to think about this as a factory. Okay, this is a factory. This is a factory. This factory is going to do something, is going to produce something. And this factory has worker number 1, worker number 2, worker number 3, and worker number 4. And these workers are very strong, super strong. They are very strong and they can do a lot of things. Now let's move on to the other factory. I want you to think about the GPU as another factory. So the GPU is going to be factory number 2. It's going to be different to this factory. This factory hires just kids. Let's say this is a kid, and this is another kid. And each one of those green tiles that you can see is going to be a kid. These kids have discipline. They obey orders and they can get things done. However, they are not as strong, and we're going to call this factory 2, and we're going to call this factory 1. So the worker in factory 1 is very strong, and the worker in factory 2 is not that strong. It's smaller, but it has discipline and is good at some things. Let's say these kids are wizards at mathematics. These guys are good. They are not bad. So the idea is this. There are going to be some tasks for which these guys are going to be great. But there are some other tasks in which these tiny little guys, if they work together, you are going to have perhaps 1,000 workers or maybe 10,000 workers versus 1, 2, 3 workers. That's the big difference. So in this size, in factory 2, you are going to have a lot of workers, a lot of workers. And a lot of workers means what? A lot of, let's call it, persons can help you to get things done. All right? To get things done. So the idea is, what do you prefer? Do you prefer to solve a problem in, I don't know, let's say 1 hour? Or you prefer to solve the problem, the exact same problem in maybe 1 minute? So for some problems, this is the best approach. Okay. So let's talk a little bit about parallelism. All right. When we talk about parallelism, we talk about two different kinds of parallelisms. We talk about task parallelism and we talk about data parallelism. So task parallelism is nothing else but when a task or a function can operate in parallel and independently. For example, let's say the first worker is going to move boxes. This is worker number 1. The second worker is going to paint the walls. The third worker, worker number 3, is going to do financing. And the fourth worker is going to, I don't know, let's say, file reports. So as you guys can see, move boxes, paint walls, do financing, and file report, all these are going to be tasks. If those tasks are independent from each other, we can assign a task to each one of our workers, and they can begin at this instant of time, and they can conclude here, all of them, because the tasks are independent. That means that you don't have to wait for this guy to finish so that this guy can begin. And you don't need to wait for this guy to conclude so that this guy can begin, and so on and so forth. So that's task parallelism. Data parallelism, on the other side, is different. Data parallelism is going to be as follows. Imagine, for example, there is a list of, let's say, a million numbers. Okay, there is a list of a million numbers. So data parallelism is like, for example, we are going to compute the addition of all these numbers, and we are going to divide this into 4 segments. So you are going to have the whole data is this. This is your data. Now we're going to divide this into 4 parts. Part number 1, which is going to be 250K numbers. Part number 2, which is going to be 250K numbers. And the same for part number 3 and part number 4. So with that being said, data parallelism is, okay, there is some data that I need to process. And we can take this problem. What is the problem? The problem is add them all together. Okay, we can add all those numbers this way. I am going to take care of this section, and you are going to take care of this section, and then the other person is going to take care of this section, and then the next person is going to take care of this section right here. And then at the very end, once you are done, once I am done, when the other guy is done, and when the other guy is done, there are only 4 numbers that need to be added. And then we take those numbers, we add them together, and we reach the final answer. So that's data parallelism. So where are GPUs very helpful? In what case? As you guys can see, GPUs are suited for this one, for data parallelism. So that's going to tell you something. Are the GPUs good and the best at everything? So now you guys are seeing that the answer is no. GPUs are not good at everything. They are really, really good in some particular scenarios. That's why it's important to understand what task parallelism is, and that's important to understand data parallelism. Now, independent of this lecture, it's always important for students to understand that in order for you to solve a problem, you need to fully understand, or at least to have a very good educated understanding about the nature of the problem. You cannot and you should not expect to properly solve a problem if you don't understand the problem. And that's one of the major sins that I have seen in many students. You try sometimes to solve problems and you don't fully understand the problem. You need to really understand the problem. And once you really understand the problem, implementing a solution is going to become much, much easier. All right. So I just told you that GPUs are not the best at everything. So what is going to happen in real life? Well, in real life, of course, this lecture is about computer science, so we're going to talk about a computer program. So in this particular case, this what we happen to have right here is going to be a computer program. So we're not going to go deep, super deep into this, because not necessarily everybody in the audience is interested in writing programs for computers, but I am going to give you the big picture. This is a computer program, and the idea is GPUs should be used. Okay, no problem with that. However, we just concluded that GPUs are not the best at everything. They are really good when the conditions are right, and not that good when those conditions are not in place. So what are we going to do? What we are going to do is to analyze our code, and we are going to say, hey, look at this section right here. This section is a section that it shows a lot of data parallelism. So what we are going to do is, hey, you know what? Instead of telling the CPU to process this, let's give that to the 1,000 or 10,000 kids so that the kids get this done quickly. Because if we give this to the very strong guys, they will get it done, but it will take them forever, maybe 10 hours. So on the other side, if we give this to the kids will be done with this in maybe 1 minute. So that's the idea. So the idea is you combine CPU and GPU. And the CPU takes care of the sequential, and the GPU takes care of those computing intensive, especially data parallelism. All right. With that being said, allow me to. With that being said, I'm going to skip this. I'm going to come back to that, but I'm going to give you something to reinforce the idea. Okay, this will reinforce the idea of the differences between one and the other. So what you are about to see, let me see. This is the audio here is. What you are about to see is how the CPU, not the GPU, the CPU, the Intel i7, the Intel i3, or the Intel i9 works. Now, the next section that you're about to see is how the GPU works, which is different, which is the element that we are going to be focusing on during this lecture.
Dr. Colmenares, you may need to change the window source.
Say it again.
You may need to change the window source. Still seeing the PowerPoint.
Oh, really? I'm so sorry. I thought you were.
Yep.
I thought you were seeing the video. Oh, you are not seeing the video? No.
Not yet.
Really? I don't know how to do that. Okay. Let me see. What are you seeing now?
The PowerPoint window. The entire thing, but not your taskbar.
I think it's because you share that particular window as opposed to sharing your entire screen.
Okay.
Yeah.
Let me try this again. Okay. Yes, maybe you just. What about now?
Yeah.
You guys see it? All right. So let's do it again.
It's supposed to be no sound.
No. Do you have sound?
I don't.
What about the other guys?
No, we're not getting sound through.
Really?
Yeah, we're saying
Yeah.
it, but no sound.
So
There should be closed caption, CC.
no, without sound. I don't understand why there is no sound. Yeah. Maybe let me do this. Okay, I think I might have a solution for it. All right. Maybe this is good. All right, let me unplug this. And to show time. Let me see where I am. Okay, here I am. Time goes like this. So this is the very first instruction that is going to be processed. So the computer is going to read this and it's going to say, oh, this is for the CPU. Let's allow the CPU to do it. So this is why you have one line here. And then you reach this point and say, oh, you know what? This is the section in which we need a lot of kids helping us to get things done. And each one of these arrows that you see here is going to be a kid doing something. And time flows like this from here to here. Excuse me. So this curly arrows is a kid doing something over time, and the kids proceed to work here and conclude their work right here. And then the kids say, well, you know, we are done with whatever you asked for. We are done, so now we can go and rest. And then it's the responsibility of the other guys that are very strong, but you perhaps you can use only one of those guys. And then maybe later on in the code, you are going to call the kids again and the kids will process. And that's what you are seeing here. So again, each one of those curly lines is going to be one of those kids doing processing for you. Excuse me. So that is the general idea in a very, very simplified terms of what is happening in a GPU. When you are working with GPUs, there is going to be a name that is going to come into place, and the name is thread. Thread is nothing else but the way that they make reference to one of your workers. So this is a thread. I like to use for presentations like this, where the audience is from different backgrounds. I like to call it a child or a kid because it's simple, right? But that's the idea. With, with let's skip this one. With that being said, it's also important to understand that you are working with two different components. You are working with component number one, which is the CPU, and component number two, which is the GPU. This CPU works with some memory, and this memory is called the main memory. So the CPU works with this memory. So memory is where you are going to store your data. And this GPU internally has some memory. And In the case of the GPU, this is going to be called global memory. And this memory is inside the GPU, physically inside. In the case of the CPU, it's not necessarily inside. It's on the side in a different component. When you are buying a computer, you always ask, okay, what processor do I have? What is the frequency of the processor? How much memory do we have? How much memory? That memory that you are making reference to is this one main memory. So what I want you to understand is this is a device and this is another device. This is a piece of hardware and this is a piece of hardware. This is piece of hardware number one and this is piece of hardware number two. If we look at this might be your motherboard. And here you might have your CPU. And here you might have your memory, several slots of memory. And somewhere in here, perhaps, you have your GPU. All of them are in the motherboard, all right? But what I want you to understand is this CPU, which is this one, is a piece of hardware. And this CPU works with some memory, which is going to be main memory, which is going to be this memory right here. And this GPU is another piece of hardware. And the global memory that I'm making reference to is inside that GPU. So how things are going to move around is important to understand that you are going to be moving information from place A to place B. And we are going to use common sense to understand the flow of the elements here. So what is the idea? The idea is to process information really fast. Do something to this information. At this point in this lecture, we don't care what. What we want to understand is we want to get something done to this information and we want to do it really, really fast. So in order to do that, we are going to work with the GPU. However, by default, all the information that we have, alias our data, which is this one right here, is going to be in main memory. But remember, you want the GPU to process that information. So what is what we are supposed to do? We need to think logically about this. So we are going to take information from the CPU into the GPU. But before we do that, there are a couple of steps that you need to understand. So the CPU is going to communicate with the GPU and is going to tell the GPU, hey, GPU, I need you to help me with something. The GPU is going to say, sure, no problem. What is what you want? So the CPU says, well, I need you to reserve space in memory for some things that I am going to send you, for some data, for some information that I am going to send you that I need you to use and I need you to process and I need you to compute the result because you are really cool and you can do it really fast. So the GPU is going to say, sure, no problem. How much memory you will need me to reserve? So that is where this fellow comes into action. CUDA malloc. CUDA malloc is the command that the CPU is going to use to tell the GPU, I need you to do me a favor. I need you to reserve this amount of memory because I need to place in that section of your memory the data that I need you to use and the data that I need you to process. That's this command. And then it comes this command, CUDA memory copy. CUDA mem copy is the command that the CPU is going to use to send information to the CPU. However, this command is bidirectional, which means that it works both ways. It can be used by the CPU in order to send information back to main memory. Right. So we're going to keep it super simple and we are not going to go deeper into that. The last command that I'm going to mention is CUDA free. CUDA free is the command that the GPU is going to use after all the computation has been done and the necessary information, the information that was processed, has been sent back to the CPU or the CPU or the memory that the CPU is going to have access to, which is the main memory. So to put this into a more familiar, simple context, let's think about this way. You have a factory and you have a lot of files that you need to be scanned. Those files are in your warehouse, your main memory. You are CPU, and your warehouse is main memory. And you have a lot of files that need to be scanned. Those files is what I have here, and we call data. Now, I have another factory. In this factory, I employ, let's say, 1,000,000 kids. So my 1,000,000 kids, each one of those kids is sitting with an scanner. So that means that we can scan your documents in no time. So what is the regular flow or the simple flow of events? You have to call me and tell me, hey, I need you to do something for me. I will tell you, sure, what is what you need me to do? And you will tell me, well, I need you to scan some documents for me. So I will ask you, sure, how many documents? You will tell me 1,000,000 documents. So I will know at that point in time if my warehouse, my global memory will have enough space to store that information. If that is the case, I will tell you, sure, no problem. At that point in time, you will tell me, absolutely great, fantastic. I will send you the information, the copy. So I will accept the copy and I will place it where it is needed, my GPU warehouse. And then at that moment in time, I will tell my workforce, my 1,000,000 kids, hey kids, take one file and scan the file. And the kids will scan the file. So in no time, your files will be scanned because each one of my kids has a scanner. And then I will tell you, well, you know, hey, CPU, I have your files ready. I need to put them in your warehouse. Give me the address of your warehouse. And then I will use the exact same command, CUDA main copy, to give you that solution, that final solution that you were expecting for. And at that point in time, I no longer need your data or the information that I process because I already gave it to you. And at that point in time, I will return the resources to the system using CUDA free. So that's is in simple terms, the flow of events that are going to happen. So it's important for you to understand the hardware and software at this point. Magali, how much do I have? This goes for 3.
You can continue.
You continue? Okay. All right. So the next slide, I'm not going to go deeper into this, but this is a very simple program when you are working with C++ or C, and this is a simple program, sequential program, very simple. What this program is going to do is nothing else but printing this on a screen. This is the same program if you go for GPU CUDA version. So now you might see the difference. Like, oh my God, this is so simple here and it's so small. And when we go for parallel, it becomes this. So the point is simple. The point is going from sequential to parallel has a cost and it has a benefit. The cost is you will have to experience a learning curve in order to benefit from the speed that you are going to gain. The idea is that, yes, going from the sequential to the parallel is not necessarily a very straightforward jump, but once you have built the foundation, it's a strongly beneficial jump. It's going to benefit you a lot. Of course, there are things that you need to put into context. If the size of your problem is such that you write a sequential program and your problem is solved in 1 minute or 15 seconds, and you are okay with it, then great. You don't need parallel computing. But if the problem that you need to process can take, let's say, 1 year, and you can bring it down to 10 minutes, absolutely you need parallel computing. Or if you are using, if for example, if you are using a piece of hardware or equipment that needs to react really, really, really fast to certain particular event, and your sequential program is spending 1 second, and maybe with parallel computing, you can bring it down to 1 microsecond, then you need to use parallel computing. And now you might say, no, there are no problems in life in which 1 second is not going to be enough. Well, what about if you are writing software for a combat airplane? 1 second might be a very long time if you are the pilot and you are going to shoot a missile. The moment you push that button, the missile or the command has to be processed quickly and right away. Maybe 1 second will be too long, you see? So you really need to understand the problem that you are about to solve. So the point is, going parallel is strongly beneficial if your problem is big and it's going to take a long time. Otherwise, you might be okay with the sequential approach. All right. So let's go for this one. This is a very simple example, and I'm going to explain it in friendly terms. So what this is going to do is write hello world on the screen. How is sequential going to work? Sequential is going to work this way. Sequential first is going to print this character, then in the next instant of time is going to print this, in the next instant of time is going to print this, in the next instant of time is going to print this, in the next instant of time is going to print this, so on and so forth, and then this. That's how sequential is going to work. So if we talk about this, in seconds, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 seconds, pretty much. Now, if we talk about parallel, then we have this perhaps in memory. And in one instant of time, this thread is going to take this and transform that into this. And this thread is going to take this and transform this into this. The point is, perhaps we are going to have 1, 2, 3, 4, 5, 6, and all this created in 7. So the idea is these were created initially sequentially, and this section was created in parallel. So we went from pretty much 13 seconds to 7 seconds, which is almost a 50% improvement. Now, I'm going to talk a little bit about the benefits of this. Let's go to the benefits. I don't think time is going to be enough, but it's okay. So, currently, we are pretty much precisely doing this through the web because coronavirus. So, coronavirus, what you are seeing here on the screen is nothing else but a predictive model for COVID-19. And this is a curve. Actually, I think this is from the, if memory serves me well, I think this is from the Thailand Institute of Technology. They wrote a predictive model, and the model, of course, is fed with a lot of information that they can find on the web and from official sources. And this predictive model is going to use a lot of the data associated with COVID-19 information per country. And in this model, what you are seeing is the model is analyzing a lot of information from this date to this date. And of course, it's predictive. Predictive means something like this. Predictive means this. Predictive means based on the current information that I have been able to identify this particular trend. If current conditions remain the same, then we can predict this. That's what a predictive model means. So according to this model, the theoretical ending of this infection for the United States is going to be November 11, 2020. Okay? You need to understand that what I am telling you is not, I am not saying that is going to happen. This is a model that predicts things based on information that is available day by day. So these things change over time. It's an educated guess. Independent of that, the point is, this is a data intensive processing problem, which means that behind this, there is a lot of computation being done. Now, if you allow me to show you this, hold on. If you allow me to show you this, can you see the paper? Can you see the info? Hello?
Yep.
You are cutting out, you know, in and out.
Well, this what what you can see. That's maybe because of the web. I don't know. Well, what you can see here is a predictive model for different countries. So for Singapore, for Italy, for Singapore, Italy, and here you can see all the different countries that they have analyzed: Brazil, USA. The point is quite simple. The point is GPUs allows scientists to do these kind of things. As you can see from the paper that I just show on the screen, many, not only just one country was analyzed, but many countries were analyzed. And they are analyzing a whole bunch of information per country. So that's the power of parallel computing and data intensive processing. With that being said, I'm going to try to share this video here. Hopefully it will go through. Can you hear?
Not so far.
No, there is no sound.
That's fine. Okay. All right. So if you cannot hear, so there is no point in showing those videos because I don't know what is going on. I mean, the audio, the problem that I have is there is a lot of feedback between the microphone and the speaker. So it's a destructive loop if I allow the speaker from the laptop to feed audio into the microphone.
I think
All right, so
if you could embed the video on the PowerPoint, it may work.
yeah, I think it's mostly a problem associated with the computer than the PowerPoint.
Yeah.
But it's fine.
Yeah.
It's fine. Well, I'm going to talk about some other benefits quickly to give you the idea. So there are many things that we can do with this GPU, and the benefits of the GPU go from artificial intelligence, climate modeling, molecular dynamics, weather prediction, and you name it, many of those. One of the things that students have learned in the class is how to time GPU applications. In the research that I'm going to be working with the students are going to be working with this, what you are seeing here on screen. There is a profiler that is created by the manufacturer and will allow the students to see things like this. What you are seeing there on screen, it shows you, for example, it shows you this right here, what you see is going to be time. So it means this is 161.7 milliseconds to 162 milliseconds. So by analyzing this information, you are going to be able to see, okay, this kernel executed from this moment to this moment. So if I compute the delta, I can find out the total amount of time that is required to be executed. And then what you are seeing here is after this concluded, this was executed. And after this concluded, this was executed. And after this concluded, this was done. And all this was done in parallel with this, and so on and so forth. So the student is going to be able to appreciate a lot of parallelism happening, but more importantly, the student can examine if this is an scenario that can be solved or approached in a different way in order to remove this from here and maybe overlap it with this. Overlapping means doing more than one thing in the same instant of time. So imagine for a second, like you can wash the dishes and with the other arm, you can dry the dishes. That would be great. We can, but imagine we can. All right. So that's the idea. The idea is it's going to take you by far less to clean the dishes. If I can wash the dishes with one hand and then with the other hand, I can dry them, I will be done in half of the time. So that's the idea. With this profiler, the students can execute the program and can look at the things that are happening. Like for example, this is the memory copy command that is going to go from the host, the CPU, to the GPU. And here the student is going to see the main copy command that goes from the GPU to the CPU and so on and so forth. So the student will see all these kind of things, and the student visually will have a tool to appreciate or to identify each one of the events occurring after the kernel is executed. And then the student will be in a position, in a much better educated position to say, hey, you know, I think I need to move this routine from this place to this place, or maybe perhaps call this function first instead of the other one, and perhaps gain more performance. So that is what the students are going to be working with me during this particular research. In addition to some other benefits, like for example, the student will be able to see the start time, the duration time, the size of the grid. I'm not going to go deeper into this because of time constraint, and the student will be able to see also how well memory has been used, like efficiency. All right. With that being said, and it's kind of sad that I cannot show you. Let me see if we can do this. Maybe I will show you the video, and I will talk as the video goes by. Yeah, we can do that for now. This is use introduction. All right, pretty much what they are doing here and what they are showing is the total amount of images that they have analyzed per unit of time. As you guys can see here, this is 3,600 images of galaxies. These are galaxies. And as you can see here, this is being done by the University of Illinois. So what they are doing? They are using a high performance computing cluster in order to process these kind of things. What you are seeing here is analysis of information associated with X-ray flux that comes from the sun. And this one I don't remember exactly. This is a lot of data comes from this synthetic leg, and that data is being fed by telemetry into a computer, and it's a lot of data. And we want to see a visualization of this in real time, and we want to process this as soon as possible. So how can we do that? With a GPU. So all the data that is being created by this prosthetic leg is fed by telemetry into the computer, and inside the computer, the GPU is going to process that information and is going to give us a real-time representation of the legs, and not only the legs, but where the pressure points are going to exist at that point in time. All right, this one is this one. It if memory serves me well, I think this one is trying to analyze what they are saying. These are going to be persons that are either voice impaired or with some other type of disability, and these are devices that are going to be recognizing gestures, and not only recognizing gestures but also analyzing voice, and they are going to say, okay, it looks like this person say hi, or this person said water, something like that. In a different video, there is a very interesting section in which the mother is blind and the mother is wearing a camera, and the mother, which and she happens to be blind, she is reading a book, she is reading a story to her son. And you might say, how is it possible that she's reading? Well, she's reading because the camera is looking at the book, and the camera, the video is being analyzed. I mean, the letters, the grammar is being analyzed, and the computer is reading things back to her on a microphone that she's going to have on her ear. And then she repeats that to her son. But it's very nice, and it's so nice. I mean, this lady is blind, not this one, in a different video. The lady is blind and she can do something like that for her son. And that's one of the miracles of technology, one of the miracles of the GPU. What he was trying to say was, I love you. You see, I love you. Now, these are real-time representation of your heart. And so on and so forth. Robots need to process now these days a lot of information per unit of second. There is artificial intelligence now that write music. Yeah, artificial intelligence write music. The music that they are playing there right now is based on that. And last but not least, this is the one that I mentioned before. This is the one associated with coronavirus. A lot of processing, data processing for coronavirus. So this, what you see here on the screen that says folding, this is called protein folding. And as you can see, this is associated with COVID. So what this is doing is running a lot of simulations on a GPU in order to, well, see how certain things behave against COVID-19. And as you can see here in this section where I happen to have the mouse, you can see that they are using only one GPU, and this is the type of GPU that they are using. And there you guys have it. That's more or less. In these times of coronavirus 19, one of the things that they have developed is these tiny robots. These robots are delivering medicine to people that need the medicine. And of course, these avoid contact with another human being, which I guess perhaps this was done during coronavirus. And this one right here is a new disinfecting device that is being used in some hospitals, which it's supposed to send a blast of ultraviolet light, which is supposed to kill COVID-19. And this is the previous one, this one. This one is a system that is going to analyze who is, not only who, but how many of the persons working around certain area are going to have the proper protection against COVID-19. And not only that, but it's going to, based on body heat, is going to estimate the body temperature. So it's like hospitals might have this in the near future. And if you are walking around with a temperature around 100, they might tell you without any person coming at you and asking for your temperature, they will come at you and will tell you, hey, you need to leave because we have read your temperature and your temperature shows that you have fever. So these are some kind of the things that are happening in hospitals, and these are some of the things that are being done now with GPUs. It's kind of sad that I cannot show the videos, but in more detail or use the original audio, but that's pretty much what I have for you today. And I hope you got to understand the basics of a GPU, what I really want you to understand is, in this world, either if you are or not a computer science person, there is a device called the GPU. The GPU is the graphic processing unit, and it was created to play video games. However, yeah, incredible. It was created, yeah, it was created to support video games. However, it was just students like you in projects like this, like Eureka, and supported by your faculty members and the natural human curiosity that we have, what took humanity to discover that, hey, GPUs are great at science, not just at video games. And it was your curiosity that has been driven students all around the world to create applications like this. And as you can see, these things are changing the world. These things are changing the things that we are going to see in hospitals and some of the things that we are seeing these days. Like, for example, all these self-driving cars. These self-driving cars, what they have is a lot of cameras connected to a bunch of GPUs that maybe they have on the trunk, because I have seen those cars. So there is a space on the trunk where they have 2 or 3 GPUs. It has to be a redundant system. A redundant system means that if one GPU fails, another one must be there and take action. So this is, that's precisely what these intelligent cars are going to be doing in the future. These cars are driving themselves because they have GPUs. Without the GPUs, it would be pretty much impossible. So I want you guys to walk away from this lecture knowing that there is an element that if in the future you are going to do computation and you are going to be working with massive amount of information and you want an answer to your problem in a fraction of the time, then the GPU is there for you. If you are okay waiting 1 day, 2 days, 3 days, 1 hour, 2 hours, then you don't need a GPU. So there is a little bit of everything for everybody. But if you are informed, wise decisions will be made. And that's the point of this lecture. So that's pretty much what I had for you today. And if you have any questions, I'll be happy to take questions now.
It was very, very well presented. I feel like we all have a very good understanding of the difference between the two of them. That was a very good job. Thank you.
Oh, my pleasure. Thank you so much for the feedback. I really, really appreciate it. Thank you.
Question: how important do you see GPUs being in the further application of machine learning? Because now there's more and more data available. So do you think GPUs will be used to feed them the data so that they can have better models?
Yes, that's a very good question. And the answer is yes. The main reason why this new field of machine learning and deep learning and artificial intelligence exploded, and even data science, is because of the GPU. If you can put deep learning, machine learning, all under the same sack, and that would be AI. Those are contained into AI, artificial intelligence. So artificial intelligence is very old. Artificial intelligence, in terms of computation, artificial intelligence is old. Artificial intelligence, they started with artificial intelligence around the 40s, 50s, and they developed a lot of theories about AI. However, artificial intelligence, this is a true story, artificial intelligence almost disappeared as a branch of computer science, almost disappeared because of 2 reasons. In order for you to do good AI, you need 2 things. One thing is data, information, and the other one is computational power. Before, in the past, the only thing that we had was the CPU. When I was in college, we had CPUs or processors with only 1 core, 1 worker. These days, you guys, most of you perhaps have an Intel i5, Intel i3, Intel i7, Intel i9. So that will give you around maximum 6 cores, 6 workers. Most of you perhaps will have 4. If you buy one of those new AMD processors, you will see that these processors now come with 32 workers, 32 cores, maybe 64. It depends on how much you are willing to pay. The point is, in the past, we didn't have that. In the past, the scientists that were working on this in the past, they didn't have internet either. So they had tiny amount of information, tiny, very tiny databases, if any database at all. And the other thing is they didn't have a lot of computational power. Now, if we forward to today's date, we have databases for free that scientists can access for free, publicly available. If you have funding, maybe you can access some of those that you had to pay for. That increases the access to the amount of data. And we have devices like a GPU that for sure is gonna crush numbers as a king compared to a CPU. That's the very first slide that I show where I told you, you know, most of the problems that we are going to solve in real life are going to be floating point numbers, not integer numbers. And that is where the GPU is keen. The GPU is keen at crunching numbers. So yeah, GPUs are going to be with us for a very, very long time until the next new thing is developed. You cannot say this is going to be forever because in computing, you never know. If quantum computing works the way it's expected to work, maybe GPUs will go away. Who knows? Maybe no. A lot of people, when GPUs were created, a lot of people say, you know, GPUs is going to make CPUs obsolete. And no, that hasn't been the case. As I explained in the lecture, part of the program, part of the routine is executed by the CPU, and the computational intensive parts are processed by the GPU. But as of now, we can say GPUs are going to be with us for a while. And yes, GPU support strongly everything that is artificial intelligence is going to be accelerated by GPUs. Yep.
Thanks.
Sure. All right. More questions?
Well, I just wanted to add that I think computer scientists have, you know, their jobs secure for a long, long time.
Yes. If we close, I have a job.
That's right, you do. and well, I'm more for the students, you know.
Yeah, I know.
You know, the market, and I know there are some engineers and computer students in the group.
Yeah.
So there is plenty to do, you know. So experiences like this,
Yes.
reinforce and, you know, make a strong portfolio so you can find a job. And yes, I think we are where we are right now is because of the human brain, right? The thinkers and the ones that can think outside the box.
Yes.
And that is developed, you know, through, you know, through times and experiences like this. And even if we don't understand all the all the details, but it is putting a grain in our mind, and we can
Yes.
develop that.
And I'm so sorry, Magali, go ahead.
No, you got you.
Okay. No, yeah, I just wanted to add that. Yeah, I totally agree with what you say. I mean, in today's world, um, these things that I just mentioned, um, is or the things that you can see is, for example, when in this video you saw the data processing of the sun, that is not done exclusively by computer scientists. I assure you that there are physicists and people from some other background, and they are using these technologies. The point or the message is quite simple. The point is, if you are in science, in today's world, you are not going to remain untouched by a computer. And if you are the new generation, like you guys, um, these kind of resources are there to give you more computational power. And the computer is nothing else but the most powerful processing tool that we have access to. So it's your decision, and it's in your best interest to add some degree of knowledge when it comes to computation. I have friends in mechanical engineering that they are really good at computation. Why? Because they are computer scientists? No, they are mechanical engineers. But why they are good? Because it's a tool. It's a tool for you to harness the potential of this fellow and make things faster. So it's like any other tool. You can use a drill, and you can put the you can use it wrong. You can put the drill bit that is not the right one for the job, or you can use it right. You see my point? So it's totally up to you. And that's something that eventually you learn over time. And let me tell you another thing. Companies like NVIDIA, they know that perhaps you are in chemistry or chemical engineering, and perhaps you don't like computer science. So they say, sure, no problem. So however, we are going to do things slightly different. We are going to create something that will oversimplify the complexity, and still you will be able to harness the potential of this GPU. So don't think for a second that all the things, all those programs that I show you, you are going to be required to write all those programs. If you are in computer science, or if you are in maybe mechanical or electrical engineering, yes, you might need to learn how to do that. But if you are in another field, these companies create libraries that eventually you can use, and you need to understand how this library work. But understanding the library is going to remove a lot of the complexity associated with writing these functions. So the point is, yes, these resources are here for you to use. And I strongly advise you, especially if you are planning to go into graduate school for a master or a PhD, I strongly advise you to look into these computational resources. If you are using a computer and you are use the processor, now you are aware that there is something better than the processor to crunch numbers. So it's totally up to you if you want to use it. But you need to know, and if you understand that it's there and you get curious about it, then my job was done.
Right. Yeah. And I just want to add one point. It turns in reference to the coronavirus, the things that you talked, and is about the the prediction, the models that can be made, with the data, and it's the amount of data that makes scientists able to build those models, right? And predict. And so even though there are predictions and they are not 100%, what is the word?
Accurate?
Well, the computations are accurate, right? But they are predictions, and life, it may go in another direction, but it is, you can then adjust your life based, or the things that you do based on an educated guess, an educated prediction, and not on, you know, what I believe, on, you know, things that,
Yeah.
you know, what I think it is, you know, because I don't know how to do that kind of computations, right? So I would rather play safe instead of, you know, listening to charlatans and you know, so listen to the people that know. So what I want to emphasize that even though we feel safe here in Wichita Falls because there are not many cases of coronavirus, we still have to exercise caution, and we should follow the rules, and so we can stay safe and healthy.
Yeah.
And so, and it's just using, you know, informed, make your decision based on an valid information, and that you can trust, and so, and use your common sense and critical thinking skills. And so I know that we are all kind of frustrated of being inside instead of, you
Yeah.
know, enjoying the sun, but we still can be outside and enjoy Mother Nature. We just have to avoid the direct contact with other humans.
Yeah.
We don't know at this point if we are carriers or not.
Yeah, it's kind of tricky to know if you don't show any symptoms and you are not taking the test. It's tricky.
Yeah, yeah.
Yeah.
So well, very good, and I hope the students also have something. They learn something that they can add to their toolkit, and for their future.
Sure.
All right. So with this, we conclude the workshops for today. So my goodness, it's almost the end of the week. So there are only 2 workshops left tomorrow, right?
Yes.
So I'll see you tomorrow.
All right.
All
And
right.
Miami, thank you so much.
All right.
And
You're
to the
welcome.
students, thank you so much for being here. I appreciate
you.
you attending the lecture. Have a nice rest of the day.